Just want to run through it real quick. So you have really three different types. You have supervised, unsupervised, and reinforcement. It's actually a semi-supervised as well in there. And that's actually reinforcement, I guess, would come under that, where it's a combination of those two, supervised and unsupervised. So let's start with supervised learning. Supervised learning is where I have a data set and I have a goal that I want my machine learning to do. I have something I want it to learn. I have a definite set of outputs, I have a definite set of inputs, and I want it to learn that relationship. So basically it iterates through a process to get to that point where it understands how to manipulate your inputs to be an exact output. And there are two types of outputs that we could have it learn. One would be classification, which very simply would be, is it a tree or not? Is it a cat or not? Is it, or taking it further, is it a cat or a dog or a bird? Those are all definitive answers to a question, yes or no. Cat or dog, it's 1 or 0 is your output. Another type of supervised learning is when your output is not something like a class of items, objects. It's a regression, which is a analog output. Analog one, a number between 0 and 1,000,000. Let's say like a price. Having it learn what's the optimal price to sell at. Let me think what else. A count of units that I'm going to sell, something like that. It's not is it this or that, it's how many, how much. That would be a regression technique, but you're still setting your output to something and having your process learn it. And there's a subtle difference between the algorithms that you use, but many algorithms apply to both. And then you can see there's different examples of each one of those types of learning. Okay, so another type of learning, so like say you don't have a defined problem to solve, definite output to learn. I just want my network to just classify things, but not necessarily, I don't necessarily know how it's going to come out with an answer. It's just going to divide up my learning data, my input training data into different classifications. It's going to just naturally see how to do that. And we'll talk about this much more. And it's basically that's clustering. It's just like, let's say I have a bunch of customer sales data and what they purchased, and I want my algorithm to just break all the customers up into 4, give it a number, different groups, and then see what happens. And that's it's fascinating what kind of information it'll come up with. It may come up with seasonal versus everyday customers. It'll come up with something. Basically that's the customer segmentation problem. And also there's this dimensionality reduction, which, say we have 10 inputs to our neural network, then that's too many, it's taking too long. And we know that some of those inputs are related to each other. So if one's high, the other one's always high. Like for instance, if we're working at a similar margin, the cost and retail of a sale would be those would be related to each other. So if we apply this dimensionality reduction to that data set, it'll combine those two inputs, which are dimensions of our data, together, and then we have a simpler model, simpler data set to feed our model, and therefore a simpler model, more accurate, perhaps. So those are some applications of this unsupervised, where we don't really know where we want to go with this data. We just want the network to simplify it, to come up with groupings. And then there's this reinforcement learning, which I'm just like, I'm so into this right now. It's incredible. It's game theory is part of it. Game ions right there. It's basically taking a robot and saying, go learn how to walk, and just reward it when it moves its foot forward. You know, when it starts to do something like walking, then you have an automatic reward system that's giving it. So it just tries different things and just throws away the things that didn't get a reward and keeps things that do have a reward. You know, it's incredible. This is, I think, going to end up being, you know, the be all and end all of AI, because it can encompass all the other areas. You know, you can apply neural networks to this, so it can learn very, very, very complex things. So it's incredible. It's anyway, can't say too much about it. All right, so that was all one part of the computing part of this, which is your model. You know, your model, and here are all the different kinds of models. Okay, another part of the computing is your model selection. So once you have your data, what kind of model do you use? Because we have, you know, a plethora, and you know, we need to choose one. Well, the answer is you don't really choose one. You start with a simple one, and then get an answer, and then you want to improve on that. So generally, you have like a flow diagram, and you start, you know, and it all starts with, okay, we've got a problem, and we have to get the data ready, you know, for that model. So you have to work through that part of it. So once you've got to that point where you're ready, okay, now I have my data where I think could be, you know, useful, then you start applying models, and you start with the simplest one, which like a linear regression, just so you can test out, is there any meaning in this data? You know, your data may not be, and most likely is not, a linear problem, which we'll go much more into that later. It may be more complicated than that, but you know, you'll be able to get some kind of accuracy, some kind of numerical accuracy out of it. So then you move up to the next level. You know, you might try, you know, just a basic tree, and then try the more complicated trees. And you know, it's an iterative process, and you know, it's just how you know, it's just how you do it. It all just kind of makes sense once you kind of get going. And I kind of picked, you know, a pretty complicated graph over here, but it's kind of get the idea of, you know, you work through a process. Is it more or less accurate? You know, you go toward a more complicated model. They'll run slower. It's kind of why you want to start with something simple, because that'll run very fast. So you know, you might get to a certain point and realize, okay, I need to really look at what features, you know, what are my inputs, and work that down a little bit to get more accurate. And then then something you can do is some tuning, hyperparameter tuning on a model. One of the more complicated models, the one that you got the best results from, and see if you can get better. And at the end, okay, or any point in here, you have to stop, stand back. This comes from defining the problem. Am I good enough? Am I good where I've got to? And if the answer is yes, then you stop. You're done. You might still keep playing with it, but if you're not there, if it's still not accurate enough, you're still too far off from what reality is, that's what you're testing. Then you go back and keep adding, keep going with your models, keep getting more complicated models. And if you're doing a Kaggle competition, then you just see how far you up on the leaderboard. If you're at the top, then you might take a rest, get some sleep. If you're not there, then you just keep going, have some more coffee. There's almost no limit to how far you can go with that, because somebody else is always going to be pushing you. And it's done when the competition's over. So anyway, so that's generally the flow of doing machine learning. And here's another picture of that. Get the data. I mean, you guys can see this over and over and over and over again, and it's just going to become your life. This pipeline. Get the data, clean, prepare it, train your model, train and test, then improve. Go back to number 3, and keep going. And then maybe back to number 2 if you know more, if you can do a little more research, put it in front of other people, to get even more improvement on your this part, the preparation of your data. And that's the EDA. That's a very big part, which we will go into that.